Yes, so yesterday we were talking a bit about boosting, okay? And in here we are talking in particular is boosting kind of surface boosting, okay? You will see that you have some other ways to give energy to the system, especially you can use artificial lift. You can try to give energy to each particular well. But here we are looking at boosting strategies or strategies that give energy for a group of wells, okay, for like for the whole system. And for that we were looking at the particular technology, either multi-phase boosting or single phase boosting. We decided to go more in detail. Multi-phase, will take some more time to explain, more theory. So that part you have to know that it exists. We have two main technologies, but we keep it, for time being out. But then we go on the compression. You have had a lot of information on Oscar, so to talk about that, and we go in detail to see that's just a very, not common, but it's a regular centrifugal compressor like the ones that we used in processing plants. We use it for all kind of applications, so we can do some calculations based on that. Okay, so I showed you how it looks like. Basically, we approximate the real compression process with a polytropic. Even though we know it's not polytropic, we know it does something strange, right? It does something like that, but we assume actually that we have a polytropic line, a polytropic process in which we go from the inlet conditions, inlet pressure, inlet temperature, all the way to the outlet conditions. Okay? And this polytropic exponent is related to something that we call polytropic efficiency, where we had here. Okay, and you can say that actually I show here some values, measure values from the test campaign they made for that particular compressor. And for centrifugal compressors, it's someplace between 65% all the way maybe to 80%, not more than that. Then we said, well, we have quite a few requirements on the compressor. Okay, it's not as free as we had on the choke. So we said one of them very important is power. Okay, the maximum power, if I get here a number that is in the order of 100 megawatts, then you know that won't be feasible. You will need too much energy to compress it. The temperature is also an issue because of different things that we have to consider. Suction pressure, we will see. Sometimes you need a minimum suction pressure, and the point has to fall in the map, okay, on the map. And you had not only the minimum rotational speed, but the maximum rotational speed that they define the two edges of the area. But also you have some two lines that they are the choke line when I reach critical flow in the passages of the compressor, and on this I have a line which you start having pulsating flow, okay, back and forth, back and forth. That I told you if you want to read more. Okay, so I say for that we close the topic. You have to practice. For that you have the exercise that you have to make. So I just want to give you on the exercise some orientation. How are we going to make it, or how to use the same spreadsheet for those calculations? Okay, so that is after you have done your calculations. That's the end of the plateau. Okay, and some people were asking, well, if you use 1 year step, right? We go 1, 2, 3, 4, and here we have 21. You will here find just a negative number, right? Okay, so what I have done here to know exactly the end of the plateau, I'm changing this number until this one is exactly 0. Okay, so now the step won't be on a year basis, but I say, well, the plateau happens in any moment between 20 and 21. To find exactly that number, I use the solver in that case to change that time until this one is 0. Okay. So that's the end of my plateau, and from there I say, well, I want to keep, because I have a commitment, right, to customers, I have a commitment to power plants, I have a commitment to Europe to deliver energy, so I want to keep exactly the same rate for as long as possible. Okay. Then I told you, so what do I have to change here to make the compression from this point, compression starts, and what do I have to change on this side? So let's go one by one and let's see. Rate remains the same, right? I want to keep exactly the same rate, so I can just drag it down. Then cumulative production, does that change the way I calculate cumulative production? No, right? Okay. The gas deviation factor of the reservoir also doesn't change, right? The way I calculate. Yeah. Then I need reservoir pressure, well rate, flowing bottom hole pressure won't change, wellhead pressure available. Okay. And now what happens, with the wellhead pressure available and the template required pressure? If you remember, we go back and we try to draw our system. We had the well, right? We had a reservoir pressure someplace here, bottom hole pressure, wellhead pressure. Then we had here another pressure that we call template. And then we had a flow line going all the way to the plem. And then we have separator pressure. And then I had here 3 more branches with 3 more wells. Okay, that was my Snow White field, the layout. So when I come here on the choke, initially here I had a choke, right? And I'm opening, opening, opening until I have no pressure drop. That means in practically that these two are the same, right? These two pressures, they become the same when I open the choke. So I just say, very easy, the template pressure will be just the wellhead pressure, right? Nothing more to say there. Now remember, for making the compressor calculation, I want to put my compressor here, okay? Because I want to be, act for all wells. Okay, that's where I'm going to put my compressor. So I said last class, I said that will be your new equilibrium point. That's where I'm going to move my calculations. Then I have to progress. I don't have to stop here, but actually I have to continue all the way here to calculate the available pressure at the suction of the compressor. And then I calculate the required pressure at the discharge of the compressor. And then actually I find exactly what I want the compressor to deliver. Okay, so for doing that, I say, well, that calculation actually doesn't change. Okay, even though maybe the compressor will make the pipeline maybe a bit shorter or it will affect, but we assume, doesn't change. So this part remains exactly the same. Okay, still separator pressure will be 30, and still the P plane required that I can call here now. We can put a slash here and just say this will be P discharge. That will be exactly the same, right? The rate is the same, separator pressure is the same, so that pressure remains the same. And the key of the template here. Now, what will be, I have to calculate to move from here to here, the pressure of the plem available, or the suction pressure to the compressor. So I'm going to say this is a mistake. It should be P plem available or P suction, right, to the compressor. How do I calculate that? Which equation I'm going to use? Remember, here we have to move from this one to this one, right? So we come here, we say, how is the flow going on this line? From here to here, right? So here we have Q. Which rate is it? The template rate, right? 3 times the rate of the. And so here I have P1, and I want to calculate P2. Yes? So P2 is my unknown. So I come here and I use just that simple equation, line P2. I have to be careful to use the right line. The flow line coefficient will be the flow line from template to plem, this one. Remember to block it, otherwise we becomes a mess. P1, what is the inlet pressure? as actually the template pressure, right? The template pressure is here. That is the same as the wellhead pressure. The rate is just the template rate. And that tells me the choke doesn't matter, okay? The choke, I can take it away. The choke, I don't have a choke anymore. It's just fully open. Or you can leave 0. The choke will be basically um, the template pressure or the wellhead pressure minus the template pressure. Okay? Open, fully open choke. Now, if we are in the compression, so this number, what I have available, right, should be less than what I require. We should be to the right side of the intersection. Okay, so here it looks fine, but it looks very small. If you see the difference, it's like 2 bar. So it seems very, very small, that the compressor has to provide a very small delta P. So what next? We have already pressure ratio, right? We know that's important for a compressor. We know we have to be inside this map, and this thing called polytropic head, it has a pressure ratio inside. Okay, so that's going to give me that, that the y-axis to see if it falls inside the map or not. So what else do we need that I told you is important? Hmm? We need the power, right? The power, we need the outlet temperature to start putting constraints on that to see if that operational point is feasible. So I will say here, let's put the T suction. Okay, I think that's given in the exercise. So let's go up here. And I think the T of the suction 67. Okay, so taking into account all temperature losses and everything, the temperature here at the suction will be 67. And I have a cooler, but for now, I will let you, so you have to, we will see how we put the cooler, but let's say initially the cooler is disconnected, not working. I have 67. Pressure ratio is nothing more than the discharge pressure divided by the available pressure. You see a very number very close to 1. And the delta P is the discharge pressure minus the suction pressure, 1.94. Now remember, to move the point from the inlet to the outlet, I need that guy called polytropic exponent, right? NP. And to have the polytropic exponent, I need the polytropic efficiency of the machine. So here you have a number. We're going to assume usually it depends on the rate, right? It had like like you remember last class, it had a curve that looked like that. Okay, but we are going to assume a constant number. Okay, just to keep your life simple and my life also. See, so we'll say that's 7. I think that's the number that the exercise gives. We have to calculate the polytropic exponent. That we do with the equation I showed you yesterday. Okay, we have to clear from here n, but I have done that already for you. If you go to Alt F11, polytropic exponent with k, the polytropic efficiency. So let's use that equation. Exponent. You have to be aware, I might make a mistake, so you have to be, with your eyes and attention quite, you have to be alert. Polytropic efficiency. Okay, and click OK. Then I can calculate with that. Then I can calculate the temperature of the discharge, right? Just using the equation that we also covered yesterday, which is this one. T outlet will be T inlet times the pressure ratio to the power of the polytropic exponent minus 1 divided by the exponent. Okay, so I think I didn't program that equation for you. Sorry. You can do it if you wish. So I will have to make it manually. And remember, temperature has to be in absolute. So that will be equal to 67 plus 273.15 times RP to the power of the polytropic. Be careful, we have to use the exponent, not the efficiency. Okay, the exponent, that's the one that describes the polytropic process. Minus 1 divided by the polytropic exponent again, close parenthesis, close one more, and that number is going to give me in Kelvin, right? So I have to subtract the, the 273.15. Now you obtain 69, which looks okay in terms of all the other things that I told you. Operation of the downstream pipeline, it looks fine on the methanol vaporization, and it looks fine also on the seals, okay, of the compressor. So everything seems to be fine on that point so far. And now I have to calculate. So let's go. If you remember, now we want to calculate power, right? So the outlet temperature, which was these conditions here, it seems that it's fine. Okay, it looks okay. Then we want to calculate power. Yeah, and the power, I need this polytropic enthalpy difference, and that equation, it's I didn't give you that equation. Oh, it's here. Okay. So I need to use that. I have RP, I have the coefficient, I have R, I need the set average, okay, inlet and outlet, and I have the T suction. So let's calculate the C average. The C average is, I have this equation that you also use it, C fact standing. And this one needs the pressure at the suction. Pressure at the suction is this one. Temperature at the suction is this one. Specific gravity of the gas, this one, and I have to block it. And unit is number 2 because it's SI metric. Once more, CFAC standing. Here I have to use the outlet temperature, outlet pressure, which is here to the left. It's actually this one. The outlet temperature, this one. Specific gravity of the gas is the same gas, and I block it. And number 2, you see actually there is not much difference between them. They are almost the same. Now with these two, I can actually calculate this delta HP, and then I can calculate the power. Okay, for delta HP, that equation, I think I have programmed for you. Let's see on the VBA. Okay, it's this one, but if you see, I have programmed actually the head, which is, if you remember what the head was the enthalpy difference divided by gravitational acceleration. Okay, so to find, I can use the same formula, I just have to multiply times g. So let's use that equation. Let's see, what do we need? It's called HP, polytropic head, and it needs RP, pressure ratio, temperature, which temperature is that? Inlet, okay, suction temperature. Suction temperature is here, but remember, has to be absolute. Be careful, has to be in absolute. And I don't think I'm making the change inside. Okay, if you see here, I'm just multiplying, I'm not changing, not making the conversion inside. So now I got into trouble. I have to put HP, RP, inlet, suction here. Then I have to make myself the deviation factor. What factor do I have to use?
Average.
The average, okay. So that will be 0.5 times this one, this one plus this one. Wait, sorry. The polytropic no is the number is not the number of stages. Okay, it's the polytropic exponent. R. What is that R? Constant for either gas. The gas constant, okay, but it's for that particular gas. And if you remember, is the how do I calculate that R for a particular gas? Okay, is the universal gas constant divided by the molecular weight of the gas. Okay, and in this case, we have to use the units of this one. We have to use it A314. I think that will be in joule, kilomole, Kelvin. Okay, and this one we have to use 16 kilogram per mole. So let's put it here, 834. You can make the exercise to check if the units match. Divided by the molecular weight, and I have to block the molecular weight to avoid issues later. But then, remember, this is polytropic head. I have to multiply times G. Okay, so I have to come here later and say times 9.81. Be careful, okay? You have one thing that is polytropic head, the other thing is the enthalpy difference. 0.4126.15. Mass flow. We have done it yesterday, right? Is the rate, which rate? The rate of the field, right? All rate that is going through the compressor. Divided by 5. Times the density at standard conditions, which is here up. And that's in days, right? So I have to change it to seconds. So I divide by 24 times 36. And I got 155. And the power, what is the power? Finally, the power, we go to our formula we showed yesterday in class. It's the mass flow times the polytropic enthalpy difference divided by polytropic efficiency and mechanical efficiency. Okay, so finally we will see if we can pump that or not. So here we have M times H divided by this efficiency times the mechanical efficiency, which is here. Okay, and one last thing, this says in megawatts, okay, because the power of my compressor it's in megawatts, so I'm going to put here 1 e to the 6. So that's 964 kilowatts. That's more than enough. Okay, I should be able to compress that. Yes. Okay, so power looks fine, temperature looks fine. What else do we need now? To see if the point falls inside the compression map. Okay, that's the last point that we need. Okay, everything, all the rest seems fine, but I want to see if the point falls inside the map. And like I told you, this map is made for, if you see here, it was tested for air, for an inlet pressure of 50 bar, an inlet temperature of, that's 15, and those were the curves. So I told you that there was, what we can do is we can either, with our conditions, we can make the transformation, right, to convert each point to my current conditions, or we can just use the same map at the test conditions, and then we can convert our point to we can convert our point to the test conditions. Okay, just using this equation. Okay, so that's exactly what we're going to make. But for that, we need this guy, which is the actual rate. Okay, we need this guy at here. So to calculate the actual rate, if you remember, what's the definition of BG? Let's put here calculate actual rate, actual volume rate at compressor inlet. Okay, if you remember, BG at any particular pressure and temperature is the volume, right, at any particular pressure and temperature divided by the volume at standard conditions, T standard conditions, right? But I can apply the same thing with the rate. So I can say that the BG at pressure and temperature will be the Q at any particular pressure and temperature divided by the Q at standard conditions. Okay, so to calculate the actual rate, I have just to say Q PT will be equal to at the suction, P at the suction, T at the suction. Remember, we like we is at the suction of the compressor. BG P suction T suction times Q of the fuel. Okay, so I need to find this guy, the BG. And I have already given the equation for you. I think the BG and temperature, the suction temperature. I have to check if I have to. I think I changed the units inside. Okay, but I have to check pressure at the suction, this pressure, and the deviation factor, this factor, and it gives me. It should give you a numbers much smaller than 1. Okay, because the volume at standard conditions is always much bigger than the volume at local conditions. Okay, at higher pressures and temperatures. Okay, so let's check again the equation just in case. G case, I think here in the, okay, so T in Celsius, P in bar, and yeah, so here I'm making the change inside. Then after that, I have G, then I have the rate of the field, then I find 283, have the rate, and now finally we go to our last point, which is after I have the actual conditions, right? I have the actual polytropic head and the actual polytropic and the actual rate. I can find the rate at test conditions and the polytropic head at test conditions. Okay, using that equation that I showed you before, this equation. Okay, so let's see. I think I have programmed that equation also. Okay, there are these two, and you see they give you the test rate if you have the actual rate. That's exactly what we want. Okay, and they give you the polytropic head if you have the test polytropic head if you have the actual polytropic head. So that's exactly what we want. Remember, we want this number if we have this one. That's the one that we have calculated. So let's do that very quickly before you fall asleep. HP test. Okay, and remember I need the HP, the polytropic head of actual, and that I don't have, right? Is this one, but divided by 1981. Temperature is this one. Okay, suction temperature. Remember, has to be in absolute. Temperature of the test is here, and I have to block it. A of my actual fluid that I have is here, is methane, and I have to block it also. The K of the test. I did the test with air, so I also block it. And I have need now just the molecular weight of the test. It's here. I block it. The actual molecular weight, it's methane, and it's here. Block it, and I got to 19. Now I do the same with the rate. Just have a bit of patience. I Actual rate that I have, the real rate that I have is this one. Temperature again at the inlet, it's this one plus 73.15. Temperature of the test conditions is this one. I have to block it. A of the my fluid, which is methane, is here. I have to block it. A of my test is this one, and I have to block it. And then I have the molecular weight of the test fluid, which was air. I block it, and molecular weight of my actual fluid is here, is methane, and I also block it. Then I go here, and actually, that's my point. Conclusion, doesn't look fine, right? I cannot operate because that's, here, that will be my minimum rotational speed. That will be maximum, and the point falls way below. So does it mean I cannot use this compressor for this application? Remember, we are now just in the first year, right? In the first year, we shouldn't have a big difference in pressure. So maybe the compressor will work because later the pressure ratio will increase, and that will tend to move the point upwards. Okay, so we should not just discard, that option initially. But how? So how do we make this point to bring it inside? If you remember what um, let's go. I think it was on the notes. Okay. Accurate Solutions, he said, well, we have this configuration, and we have here at the inlet of the compression station a choke. And we can use artificially to just decrease even more the inlet pressure, right? So that might be an option, okay, that I have to try. But I have to find a way to bring that point inside. So let's try that option first. So how do we do that in the current layout that we have in our current Excel sheet? Hmm? Which pressure do we have to reduce? Hmm? The inlet pressure, right? So I can just say, for example, I'm going to do it here the bad way, okay? You have to do it the proper way. You have to put another column and say pressure after the choke, the inlet choke, okay? So here I'm going to make a trick because I don't want to mess with my sheet. So I'm just going to say, is that pressure minus, and what delta should we use for the choke? We can just try, okay? Let's say maybe 30 bar, okay? Let me put here just 30 bar. And if I did my calculations correct, now that number should increase. Okay, if you remember before it was 200 and now it's 5. Okay, so now let's see how everything changed in the map. Much better. Okay, now the point moved, like in the region. But what is the problem here of this point? You are in the choke line. Okay, the choke line is the line that joins all of these points, and you are a bit outside. Hopeless, right? So drop this compressor. Doesn't work. Or how else can I bring that point back inside? Okay, so let's try that. Let's try 20. Okay, still refuses. Okay, what else can I use to bring that point inside? The flow rate, but I don't want, right? I don't want to touch the flow rate. I have a commitment. I installed this compressor. I said to my manager, it's going to work, so I have to make it work. What else can I use at the inlet? Temperature, okay? Remember, here we can control, here we are designing so far to bypass this guy. But actually we have this cooler here that we can use to bring that point inside. So how, remember that cooler I told you in the case of Oscar can go all the way down to 20. And here is also the same, so I use the same number. Here we can reach the minimum temperature will be 20. So let's see how temperature affects that. So here instead of using, and again, you guys have to do it correctly. Here is T suction, and you have to put a T at the discharge of the cooler. You have to put another column with the discharge of the cooler. Here I'm just going to change that number, and I'm going to put 20. So the rate change, the polytropic head also change. Okay, victory looks like. It's barely inside on the line, but it's inside the map. If I want, how can I make it, a bit better inside the map? How can I put it a bit better inside the map? Maybe changing a bit the pressure ratio. Okay, so here I can put again maybe 30. And now it's a bit success. Okay, managed to put the point inside the map. Yes, any question? So for the next years, okay, that's the exercise you have to make. You have to expand what we have done here for all of them. Also remember, here we're plotting the whole rate like if it was going through one compressor. But actually we have two compressors. Ackers gave the option to have two compressors in parallel. Okay, in that case, what you will have to do is the pressure ratio going to change of the compressor? Of each compressor when you have two? No, right? Because you have the same. Here you're calculating from the phlegm, from the separator to the phlegm, and that depends on the rate of the field. Okay, and here you're calculating from the reservoir all the way to the phlegm, and that depends on the rate of the wells. Okay, so the pressure ratio of these two compressors will be exactly the same. What is going to change is the rate. The rate will be half. Okay. So be aware of that. You have also the outlet cooler, and those are your tasks. Okay, to verify that if the point falls inside the map. Here I say if it doesn't fall, you can use the inlet valve to choke to bring it inside. You will need that especially for the first years. You can use the cooler that you will need when the temperature at the outlet starts getting too high. Okay, the temperature here starts getting too high. You will need to cool. And also, to reduce the power that you need. And you can use a single compressor. That will be the cheapest, but maybe because of the rate you won't be able. You can use two compressors in parallel, or you can use two compressors in series if needed. Okay, and we want to produce, I think, for as long as possible. He says you have to calculate until year 28. Okay, any question? And it's a bit we're using dry gas. It's a bit simplistic, but shows you all the additional when you're planning for an extension of the plateau based on compression, based on boosting, all the additional constraints you have to take care of. Okay, power, very important, then temperature, and then to fall inside the operational map. Okay, so to not only that I say here and I show a bit how to do it, but you have yourself go inside and try to make it work. If you don't find any other option, if you already tried with all the options, then the only option is to reduce the rate. Okay, but that you don't want. You want to keep the rate for in plateau for as long as possible. Okay, but if there is no other option, then you have to reduce the rate. Okay, wow, 1 hour. Yeah, so let's take a break. Let's say 15 minutes, and we come back, and I'm going to give like about networks. Okay, so far in the Snow White example, we have said that all wells are identical, and we can analyze on a single conduit basis. But now I'm going to give the more general description: what happens when each well is different. Okay, how do you calculate them? So let's go. That will be the second part of the lecture. Any question? Okay, so let's talk about surface networks. Okay, exactly the same case where we have, for example, two wells. Okay, but now the wells are not identical, so we cannot make that assumption that just the assumption that Q well will be equal to Q of the field divided by 2 is not valid. And that's basically the common case when we already at the later stage of development of the field, we already can know that each well won't be the same. The tubing length will be different, the depth will be different, maybe tubing size will be different, the deliverability, the characteristics of the formation will be different. Many different cases, maybe the fluids will be slightly different, so that assumption is not valid anymore. So you have to go into to solve exactly how much each well is producing. For that, I say first we do it graphically, and then we go a bit on the more formal way to make it. Okay, so what I'm going to say, I'm going to divide that system in three parts. Okay, first, let's say open choke. Let's make first that assumption, open choke. And I'm going to take a system called 1, that will be my well 1. I'm going to take a system called 2 all the way to the junction. Okay, well 2. And then I'm going to take a third system, which is just the pipeline. Okay, and pipeline. And I'm going to plot, as seen from each one of these subsystems, I'm going to plot the pressure at the junction. How does it look like depending on the rate? Okay, so I'm going to first to start well 1. Okay, let's say well 1. And the well 1 looks something like that. And here I have a P that I'm going to call junction, and I'm going to put just 1 to be sure that that's the has seen from 1. It will be the same, right? But I'm looking from different locations. So if I were to plot the versus the Q of the well 1, okay, the rate of well 1, and this P junction 1, how is it going to look like? First, what pressure is that? That's the available pressure at the junction, calculated co-current from the reservoir pressure of well 1. Sorry, that's well 2, right? Sorry, that's well 2, 2, 2. Sorry, because we're looking at this well. So that's well 2. So that curve, I have to go from reservoir pressure 2, bottom hole pressure 2. There I go up to wellhead pressure 2, and then I go to junction 2. I may have potentially to use an IPR, a tubing equation, and a flow line equation. Okay, but it looks, no matter how you calculate, it looks like that, right? That's how it's going to look like. That's how I told you, and that's how you're trusting that the available pressure curve looks like. Okay, always going down. Now let's go to well 1. Okay, so that's well 2. For some reason, we decided to start with well 2. Well 1, how is that pressure going to look like? Pressure junction 1. if I make the plot of pressure junction 1 with Q of well 1? Exactly the same, right? So it should look, this is the available pressure at the junction. So it should look like that, right? And you know how to calculate these curves separately. Now, if I go to the pipeline, how is that curve going to look like? Okay, and the pipeline, it's this one. Okay, and here I have P junction pipeline. Now I don't use the rate of the well 1 or well 2, but I use the rate of the field, and I use P junction P. Okay, P junction has seen from the pipe. How that's going to look like? Just going up, right? The required pressure at the junction. But there is one catch, right? All of these pressures, they should be the same. Okay? So I should find, so if I say all of them are the same, right? So I say I use this pressure star, okay? I don't know how much it is, but I say that is the pressure that I have. I go and I read this QW2 star, then I put it also here. That line was not exactly horizontal, sorry. Okay. Then you have P junction star, and then I read 1 QW1 star, and then I have here P junction star. I'm assuming, okay, I don't know, but I know all of them should be the same. Q field star. How do I know that that's the correct pressure?
The sum of the well rates.
Compare the rates, right? That's the last equation we need, which is just conservation of mass. So you say Q of the field is equal to Q well 1 plus Q well 2, right? So I have to verify. So the here, and I think some years ago we had an exercise on the exam that it was exactly doing this process. If so I assume the process will be, if I'm going to solve it graphically, assume Pj, okay, then calculate QW1, QW2, and Q of the field, and then I have to verify if QW1 plus QW2 is equal to Q of the field. Yes, then I have the solution. No, then I have to assume again another pressure, and I have to repeat the process until I converge. Okay, an iterative process. That clear? Yep. So what is, if we are going to make it analytically, let's make again that box, okay, where we had the system. So we have the number of unknowns and the number of equations. Okay, and let's start first with, from let's start from the reservoir all the way to the separator. So what equations do we have here? We have the IPR, right? If we are saying is gas, we have QL1 C1 PR1 squared minus PWF1 squared, and QW1 W2 C2 PR2. They might not be producing from the same formation, right? So to the power of n. So how many unknowns we have here in this equation, the IPR equation? We have reservoir pressure, right? We have the C and the N, but we don't have neither the rate, not the flowing bottom hole pressure. So we have two unknowns and one equation, right? And then here again we have the same two unknowns and one equation. Yes? Now we move forward to the tubing equation. How does it look like? The tubing equation, QL2 equal to PWF2 over e to the s2 minus PWH2 squared 0.5, and I have CT someplace here, right? Yeah, that equation is that equation correct? I think so. Okay. So what do we have here in this equation? We have the rate. We already have it, right? In one of the others. So we have the rate is not a new unknown, but we have, and the flowing bottom hole pressure, we also already have it. So that is not a new unknown, but we have this new unknown, which is the wellhead pressure. So we have one more and one more equation. Okay, then we do the same for well 1. Okay, and again the same thing. We have only one additional, which is the wellhead pressure, and we have one more equation. So it looks like we are catching up. We still have 6 unknowns and 4 equations, but we are, slowly catching up. What else? What other equation do we have? We have the flow line. I, we have the flow line from here to here, right? Flow line from here to here. So we have IPR, IPR, that will be TPR, TPR, and that will be flow line FPR 1, 2, 2, 1, FPR 1, and FPR 2. And that equation, if we assume horizontal line, how does it look like? QL1, CFL1, P wellhead 1 minus P junction squared to the power of 0.5, right? How many unknowns we have? New unknowns we have there? One junction. And how many equations? We have just one equation. Now the other flow line equation. Okay, how many more? None, right? Because I already had well 2. Well 2 was introduced here. Wellhead pressure was introduced here. P junction was introduced here. Okay, so I just have 0. No new unknowns. But I have one more equation. Looks promising. So I have now the pipeline performance relationship, which tells me that the Q of the field will be C pipeline P junction squared minus P separator squared 0.5. How many unknowns? The Q of the field, right? And one more equation. So how much is that? The final countdown? 5, 6, 7, 8, 7. Okay, more unknowns than equation. What else am I missing? The mass conservation. Okay, that Q of the field is equal to Q of the well 1 plus Q of the well 2. So here I have one more, 0 new unknowns. I have already Q of the field and the well, and I have one more equation. So that gives me 8 and 8. And I can solve that system of equations using any method you want. Okay, you can use MATLAB, any tool that you want. You can use Newton-Raphson. You can use any method that you want. Okay, when the expressions become more complicated, but it's exactly, you're trying to do exactly the same. Okay, it's trying to solve exactly the same. That clear? Yeah. Okay. So now I want to call your attention to something else. So let's say, so that's a calculation, and here we're calculating to compute, this was how to compute the natural equilibrium point of this system. But remember, also like in the single well case, we had two ways to calculate, right? One of them was that I want to find exactly the equilibrium point, and the other option was I remove that object that allows me, if there is any object that allows me to control the system, I can remove it, and then I can just perform the computations upstream, computations downstream, and then see what will be the delta P, right? If I had a choke. You remember that, right? We did it on the single well. Can we do it here in this case? So let's say fixed rate calculations for network. Okay, and let's take again the same example, okay, just to make, so we have two wells, these two wells, but now we're going to make one assumption. We have a choke, right? But this choke, so we are going to assume that the distance between the exit of the choke and the junction is very short, such that we don't have to use a flow line equation, but basically we can say that flow lines, let's put here, flow lines is just an assumption to make our life a bit easier, okay? Flow line uh, length is very short, such as um, the pressure downstream the choke is equal to the P of the junction, okay? Just assume that we're going to make it very short, and you will see now why, because we can make, we can solve it graphically. So if I give, okay, I'm a reservoir, let's say I'm a very, powerful and knowledgeable reservoir engineer, and I say I want to produce, because of recovery factor, because of different things, I say I want to produce exactly, I want a Q well 1 star and a Q well 2 star. I got those rates that I have to produce. Reservoir engineer, which is like God said, okay, I tell you, you have to produce these two rates, okay, given by reservoir engineer. So how can we see if we can produce those rates or not? If we have a system with two wells that I have a choke, I have a surface choke, okay, I can just come here with the two same curves that I had, right? So I know, let's say here, I know this system, I have the curves for these two systems, right? And I know how they're going to look like. Okay, for well 1 is going to look P at the, in this case it's not the junction, right, but it's P at the wellhead 1 is going to look like that, right? And then I go and for well 2 P at the wellhead 2 will also look like that, right? We just discussed it now. And then we have for well 3 for pipeline, I have this curve, and here we have the Q of the field. Now is the opposite way, okay? I'm taking out the choke from the analysis, okay? That's the way we said that's good for design, okay? That's the way. We don't know exactly which choke, we don't know exactly what model, so we take it out of the figure, and then we see if we can produce that rate or not. So exactly like we have done in the single well case, we come here, we say Q well 1 star, and we read from here what will be the available wellhead pressure from this plot, right? So I come here and I also say QW2 star, and I read what will be the available wellhead pressure. And then on the field, I do exactly the same. Here will be Q well 1 star, and I read P junction star. Now I ask you, how do I know that that rate that the reservoir engineer told me that they want to produce is feasible or not? If I can produce it or not? The simple condition that the choke requires, right? What is the simplest condition that the choke requires? Pressure upstream the choke must be greater than pressure downstream the choke. Very simple. Choke is very friendly with students, with us. Okay, we can just say has to be positive, nothing else. Compressor becomes a bit more tricky, but choke is very simple. You have to be positive. So the rate will be feasible. The rates will be feasible if and only if PWH1 star is greater than P junction star, and if PWH2 star is greater than P junction star. If not, if I find a negative number, I have to go back to this reservoir engineer and say, sorry, we cannot produce that rate. Either you give money to put a compressor, or we can increase, maybe make a more productive well, but we cannot produce that rate with the conditions that you want. Okay? You see the two ways. One of them, we had an iterative process to solve the natural equilibrium, okay? And the other one, we are fixing the rate and we are finding if we can deliver that rate or not. Two different ways of thinking, two different ways how we can apply that knowledge. That clear? Yeah. Okay. I hope we have time to make the exercise. Um, okay. So I'm going to ask you now to make another one more step. Okay. When I have chokes. So when I have chokes in the system, there is multiple combinations of rates of well 1 and n 2 that I can achieve. Okay, there are multiple combinations of Q1 and Q2 that can be achieved. Right? You understand? Because if the reservoir engineer comes with any other two combinations, as long as they give positive, I can produce that rate, right? So they are not only a unique, it's like the same thing that we had, when we had the single well case, okay? If I want this rate, or I want this rate, or I want this rate, all of the rates, I can produce them because all of them, I just have to choke. So I can really reach from any point here down. When I have two wells, it's not so simple. Okay, it's not only that. So how the plot looks like. So we can see, we can like think of the network, okay, like a big function. Okay, network, it's a function. Okay, let's put it here. Maybe it's it's a vectorial function, and that function, mathematical function, and here we have one input, which are the characteristics of the network, of the production system. Okay, and here we have basically IPR, we have the C, we have the N, we have CT, we have everything we need to make the calculation, right? And then we have another input, which is user defined, which is variable, right? We have here one thing, which is the choke opening. Okay, and that's something that I decide. So that's adjustable. And if I, let's say I choose, let's call this choke opening CO, right? 1 and CO2. If I say all of them fully open, 100%, then I will find here a rate of wheel 1 and a rate of wheel 2, right? If I say 80-100, I will find other equilibrium rate, right? If I have changed here to 20-20, I will find another equilibrium rate. So I just want to show how, if I make a plot, okay, of the feasible rates, if I say here Q well 1 and Q well 2, when the chokes are fully open, I get a point here, okay? That will be 100%, 100% open. I get this rate and I get this rate. What happens when I leave, let's say, well 1, the choke here, so let's say choke 2 open, fully open, and choke 1 I start to close. Okay, what do you think will happen with that? Where I'm going to be operating? Hmm? If I start to choke the rate of 1, okay, then the point is going to move like that. Okay, I will have less rate from well 1, but maybe well 2 will have more space in the pipe and we'll be able maybe to flow a bit more because 1 is not competing against it. They are, both of them are competing in this pipe. Okay, so if I reduce one of them, the other one has more place to flow, okay, and it can flow more easily. So usually you have an increase. So here I'm choking, 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 choking on that direction. I'm going to be choking uh, well 1. Yes. So you see that's like the limit of that area. And then I can make the same analysis. I can do the same. So let me just put that up here. Okay. And then I go choking well 2, okay, with well 1 open. And I will do exactly, will find a curve exactly like that. Yeah. So all the points that fall inside this map are feasible combinations. Okay, these are feasible rates. That means if my reservoir engineer wants this point, it will be possible to produce. You have to. There will be just one opening. Just I have to choke in that case both, right? I have to choke both 1 and 2 to reach that point. But it will be a feasible operation rate. If I want to, if my reservoir engineer tells me I want to produce here, no way, right? Because that's outside. So this is the feasible rates, and that's the non-feasible rates. Okay, all the area outside. Now I have to, let's make it a bit more realistic. Actually, the plot looks like that. Okay, it doesn't go all the way to the axis, but it looks something like that. And do you know what is the reason for that? When you choke too much well 1, okay, there comes a point that it cannot produce anymore. It just shuts in. Okay, so you have a jump. Basically, it's not a smooth transition, but basically you have a jump below certain rate. The well cannot compete anymore against well 2, and it will shut in. Okay, so actually the area looks something like that, but that's not important. My intention was to show you that you can watch the network like a function, that depending on the choke opening that you use, you will get different rates, feasible rates. Okay. Okay, so let's make an exercise now in the last 15 minutes. So you can all, I think it's on my website. It's on my website. It's class files, and we have the folder for today, and it's called Network Ulfax South, and that I think was appeared in an exercise in a set exercise set from 2 years or last year maybe. Okay, so please open that. Okay, it's this one. Okay, and the problem is we are looking basically at those two templates of Woolfax, M and L. I think M has 4 wells and this one has 3 wells, and they are competing in a flow line, and then they go to a main pipeline. Okay, so we want to calculate the natural rate that is if the field is producing in decline, already the plateau finished. So we want to calculate the natural flow through this system. Okay, and we're going to make the assumption we don't want to solve all 7 wells. Okay, then will be a huge system of equations that we don't have time to make it in class. So I'm going to assume that all wells in this template are identical, and all wells here are also identical to find the rate. Okay, so that's our problem. Um, here, last exercise. Okay, so let's see what do we have in our Excel sheet. We have all the equations we need. We have reservoir pressure. We have, can put it a bit bigger. Okay, we have separator pressure. We have the inflow part. We have the tubing part. Then we have the flow line. Okay, this system has a flow line going to the tow head, and then it has a long pipeline. Okay, so we have the pipeline, the 2 flow lines, and then we have the tow head. And of course, you have 4 wells in one template, 4 in the other template. So what do you think? I know I have to make an assumption. Okay, it's an iterative process. So what do you recommend to do first to tackle this problem? You know that you will have to assume a pressure, right? You have to, in our case, on this graphical, we assume junction pressure, but we have to assume either a pressure or a rate. Okay, and then we have to verify that the pressure seen from all sides is the same. Okay, so which point are we going to use now for our equilibrium? The tau head, right? Is the natural choice. We have do co-current calculations all the way here. We do counter current calculations all the way here. Then we do co-current calculations all the way here, and from there also here. And we see that the pressure is the same. Okay. If not, then I try again. So the tau head, we agreed that's the point we want to analyze. Okay, so what would you assume, rate or pressure? Rate. Okay. What's the problem with rate? Assuming rate. Let's say here we say we have the rate of the 2 wells. If we assume one value in each, then we already have the rate of the field, and then we have everything, right, to compute. We can go from reservoir of template M all the way to the tau head, reservoir template L all the way to the tau head, and we can go with the rate of the field from the separator to the tau head, right? No problem. But what is the problem by assuming the rate? I'm going to give you a clue. Let's put one equation, the IPR equation, for example. Okay, Q of the well 1 will be C1 PR1 minus PWF1 to the power of n. Okay, so now when we are assuming that, we want to calculate PWF. So we have QW1 C1 Um, okay, that's how we will calculate, right? The pressure at the bottom hole. What is the problem with this expression? If we are assuming the rate, okay, what could happen if I make a bad assumption?
It can be imaginary number.
You can get a negative number, right? Then you have the square root of the negative number, then crashes. Okay, the whole solving process, if you have a complex number, goes to nothing. So what will be another way that I can make the more user friendly for an automated process, the solving process, the equation, the solving equation? I can just start with, I can just assume pressure, right? If I come here and I assume pressure, I know that this pressure is bounded. I know the bounds of that pressure. I know they go from reservoir pressure all the way to zero, for example. Okay, but I know the bounds of that pressure. So by doing that, I avoid this particular problem. So that's why I prefer that we, in this particular case, we try with reservoir pressure. Okay, so let's see. Which value do I assume for flowing bottom hole pressure? Let's try something a bit close with reservoir pressure. Okay, 120. Here we try maybe with 90. Now I have to move. I have assumed bottom hole pressure. I have to calculate the rate. Okay, and for that I use that equation IPR rate. I want to calculate the rate, and I want this C. I need the N. I need reservoir pressure, and I need the bottom hole pressure that I assumed, and I drag it down. Okay, I'm now at the bottom hole. I have to move up to the wellhead. Okay, and for that, which equation I'm going to use? If you remember, it was tubing. Should I use tubing P1, P2, or Q? P2, right? We have the pressure at the inlet of the tubing, and we want the pressure at the outlet of the tubing. So tubing P2, and that needs the CT, the SP inlet, which is flowing bottom hole pressure, and the rate. Yeah, and then I drag it down. Okay, that's for a single well. Now I know that this template actually doesn't have just single well, but that one has the three, which are the same. Okay, so the Q of the template will be just this rate times the number of wells that template has, and that's actually the rate flow line. Okay, the flow line is carrying not the production of one well, but from all of them. Okay, then I'm ready to calculate again from here to the tau head. Which equation am I going to use? Okay, I think we call it line, right? P1 or P2? P2. Here we need the C of the flow line, pressure. What is the inlet pressure? The wellhead pressure, right? And the rate, I have to use the rate of the template, which is the rate of the well times the number of wells. So you see there is actually very little pressure drop between the wellhead and the tau head. And they are different. Okay, remember these two, they should be the same. They are different. That means the assumptions I made were not exactly correct. Now I'm going to move from separator all the way to tau head. Okay, for that I say, which equation do I use? Line P1. Okay. C of the pipeline. Okay, P2 will be separator pressure, the rate. Okay, I didn't calculate, but it's the sum of these two. Okay, so I'm going to calculate here. So I will put it there. I will say this the sum of these two. Okay, they are not the same. How can I make them the same in Excel? Solver, right? Seems like if I have to do many runs, many trials, I can use the solver. But how do I make that these three are the same? Remember, solver, I have just one cell. The difference between them, but if it might give you one is for example, one might give you a negative number.
Square root 0.
The square root, that's an option.
Least square.
Least square.
Oh,
Let's use a bit simpler approach, and then if you want on the exercise you're going to get for after Easter, you can use whatever you want. Okay, but I'm going to use this approach. I'm going to say I'm going to calculate an average, okay, of these three pressures, and then I'm going to calculate the deviation between that average and the individual tow head pressure, okay, squared. I'm going to say that will be this one minus this one squared, that one minus that one squared. At the end, I will have a compound error, will be the sum of all of those errors. Okay, that's just one technique. Like I said, you can use any technique you want to make it equal. Okay, and then I say solver, what do I have to set up on the solver? Please drive that number to 0, right? Such that there will be no deviation with respect to the average. That means all values are the same. By changing the only thing that we have assumed so far, which is that PWF. Okay, so let's see if it works. Change that number. I want to drive it to 0. Okay, minimum will be the same because they are squared. And by changing these two, and I can give some help, okay, to the solver. I can say, well, this one has to be less or equal than reservoir pressure. Okay, you cannot try with 150, for example. Will be non-logical. And another one is that this pressure should be also less equal than that number. And I solve, and it gave me an error. Okay.
I think you forget to lock the average pressure when you calculate the error.
Okay, yeah, that's very correct. So this one should be blocked.
The other one.
This one, and oh, sorry, it's, yeah, not this one, but this one. That's very correct. Okay, now let's see if it works, if that was the issue. Okay, that's the solution. Each well is producing 1 million. Sorry, yeah, each well is 1,500,000, and the tow head will be 66. Okay, what happens if it doesn't converge? Remember, any solving process, Newton-Raphson, you need a good seed. Okay, so that means the seed is not good. So you have to maybe try by hand to approximate a bit better to minimize that error. That clear? Yeah. So that we finish with networks. You will have an exercise on networks. Network usually, many systems we cannot analyze on a single well basis, but we have actually a network that we have to solve. And the network is, a bit complicated to solve, requires a lot of mathematical iterative processes. But at the end, what you have to keep, because you will be practicing petroleum engineers, is what is the consequence of the network. Okay, so I hope I managed to convey some of that on this part. If you visualize the network like that, it will make your life much easier. Then how you solve it, how you compute those rates, they are feasible or not, that's another issue. Okay, you can do that in software, you can do that whatever. There are different methods, but the thing is that you understand how the network works. Okay. Yes. So yeah, enjoy the rest of the week and see you next week. Hmm?